I start with, folks? Which lesson?
Optimus Prime.
Optimus Prime. Cool. Right, let's have a look. How many questions did I give you? Oh, just 4. Are you ready? A mobile phone requires only 11 volts. The mains provides 220. A transformer is used to step down the voltage. The number of turns on the primary coil is 22. How many turns are on the secondary? So, we have N1, which we don't know, over 22 equals V1 over... Alright, so that goes in there 20 times. Is it 440?
Yeah.
Alright, well that was easy peasy. 2. An electric car requires 1,100 volts. The mains provides 220 volts. The number of turns on the primary coil is 110. What is the current in the secondary coil if the mains provides 13 amps? Okay, so N1 over N2, which we don't know, equals V1 over V2, which equals I2 over I1. Okay, so I can just use this. 13 times 220 over 1100. Did you get 2.6? Okay. 3. A power plant sends 10,000 volts to a town. A step down converts it to 200. Okay, so V1 over V2 equals N1 over N2. What am I asking for? What is the current? Which equals I2 over I1. I1. So I should say this equals this. I get I1 equals 200 over 10,000 times 13. So I should get a really small number. A quarter of an amp. Four. A transformer with 100 turns in the primary. Come on, dudes. And 10 turns in the secondary is 90% efficient. The primary supply is 220. So that's V1 over V2. Yeah? Now I can get the V2. What's that? 22 volts. Now the problem is the current is not following the previous law, because if you remember the law that says N1 equals N2 equals I2 over I1, that's coming from the law that says power in equals power out. But this is not true, because I said it's 90% efficient. So instead I need to say P2 over P1 times 100 equals 90. Yeah? So I get P2 times 10 over 9 equals P1. So I can get I2 V2 times 10 over 9 equals I1 V1. Yes? Do I know the V's? I do. What am I asking you for?
I2.
I2. I know the I1. I1 is 1. So that's a 1. So then I2 would be 9 over 10 times V1 over V2 times I1. What's V1? So this is 10, isn't it?
Yeah. 11.
No, I mean the V1 over V2.
Yeah, that's 10.
It's 10 because it's 22 over 200. Yeah, so that's a 10. So is that 9 over 10 times 10 times 1?
9.
Yeah, 9 amps then.
What? But isn't that like do everything the times 0.9?
In the current and the power.
Yeah.
Yeah. 10% of it is lost through heat. Yes.
It's 9.
Yeah, isn't it? I think so.
What? Why?
Write that down.
10 over 9 and 9 over 10. 10 over 9, but it's going to other times, so it's 9 over 10.
Yeah, I rearranged this.
10 over 9 here.
Yeah, 9 over 10 on the other side.
What? What have I done?
Come on, Mr. 100, this should be easy peasy for you.
Power 1 is 90 or 100 I2V2, right? And then I just stop it.
You okay, Jerry? Do you need to close the window?
No.
Are you sure?
Yeah, but
What
I
is the
mean,
difference?
no, I mean, you put here, but he put here first, and then he changed to 9 over 10, so you're correct.
But it should be correct, right?
Yeah,
Teacher.
but, no,
What?
I mean, it's not correct, because this one,
I didn't do anything wrong there, did I? It's all good? Okay, so I'll continue. This guy here, really, he's a problem. What's wrong with you, man?
orange is wrong, but.
I haven't got time for this nonsense. Come
I
on.
mean, it's orange,
Children.
yes, wrong.
Okay, next.
Isn't it the same?
Coulomb's Law.
This one first?
Coulomb's Law. Coulomb's Law.
Yeah. Huh?
Right. Children, please. Oh dear. This will be one messed up family. Alright. 2 electrons are this distance from 4 protons. The electrons will be drawn to the protons by a force. Find the force. Right, so the formula is 8.99 times 10 to the power of 9 times fraction. On the top, what have I got? 2 by 4. So the total charge is 8. 2 by 4. Q1, Q2. No, it's 8.
You're adding.
No, I'm not adding, I'm multiplying. I am multiplying, Monica. Multiplying.
I know, yeah.
Q1, Q2 over R squared. So this is 2E, and this one is 4E. So together, 8 what? No.
It's good.
8E squared.
Oh, it is squared.
Good heavens. 2e times 4e over the distance squared. Okie dokie?
Yeah.
This is the force for part 1. Will we make it micro? Of course we will. No, we'll make it nano. No. I'm getting confused. Let me go back to the original answer. Right, this is... What the fudge?
Go with
No, leave me. Leave me. I can do this. Right. 228 nanonewtons for the first one. Can you write that down or check? Yeah. Right, number 2. An electron is orbiting 2 protons. What is the velocity of the electron? Okay, we'll have to do a little bit of maths here. So we have V equals omega or. Do we know the or? We do. Do we know the omega? We don't. But we do have F equals M omega squared or. Yeah. And then we also have F equals K M. Now the small m can be for... Sorry, thank you. Thinking of Newton. The small q can be for the electron, and the big Q can be for the 2 protons. Okay, so we have a big Q and we have a small q here. All over or squared. If I put these together, I can get m omega squared or equals k q q over or squared. The omega squared equals k q q over m or cubed. So what does the omega equal? It will be the square root of this. We're looking for the v.
Yes,
OMG, you are right. Oh, well, it's too late now. Well,
No, you're not.
it's not too late.
allowed.
Okay. Alright, fair. Yeah, I see what you're saying. I should have kept it as... I guess that's what I was thinking when I made the question, I suppose. mv squared over or, and f equals kqq over or squared. So I get mv squared over or equals kqq over or squared. So v, so actually I don't need this. So v equals square root mkqq. That's it. Just root of that, isn't it? Because, oh no, over or. Because I can cancel one of these with that. Oh, I'm sorry. There.
Yeah.
That's fine now. Are you sure it's not? It looks fine to me. KQ. Yeah, okay. Amazingly. Right. 8.99 times 10 to the power of 9. And what is the Q? It's an electron.
Yeah.
And what's the big Q?
2
2 electrons. So just for you, Monica, I'll separate them. 2 electrons. And then the M is the mass of a electron, which is number 3. And the radius is 3, isn't it? Okay. And the radius is 10 to the minus 10. So, should this be big or small? Well, I think it should be big because the electron is zipping around the proton. How big? Pretty dang big. Pretty dang big. So if you thought Mars was moving fast, this electron is doing 2,251 kilometers per second. And you are all like, oh, Mars is so fast, 24 kilometers a second. Get a load of this electron.
What is escape from
Because the electron escaped from Earth. because it's going so fast. Well, the reason it's going this fast is because of the how close it is to the proton. As it moves further away from the proton, it will be travelling slower. I think. No, you're right, sorry, it will be travelling faster. But if it moves far enough out, it becomes freed, and it no longer feels the effect of the proton, so it no longer orbits the proton. Anyway, it's difficult for the electron to escape Earth because there's so many things it can hit into on the way up. It can hit into an air molecule, someone's head, the table. It just doesn't have a good chance to get out. I suppose the electron could escape Earth if it was a vacuum. If there was nothing around Earth, if there was no air, it could just escape. But because of the air, it will probably hit an air, oxygen or nitrogen on the way up. Or someone's head, a piece of carbon, yes. Okay. You got this? Yep. An electron is trapped in an orbit around a proton. How much energy is required? Okay. So, in other words, the question is basically what's the potential energy? That's all it really is. So the formula, I'll put in the minus straight away because I know it's trapped. I have the K. The distance is 10 to the minus 10, no squared for potential energy. And on the top is a proton and an electron. Yeah, I'll have to convert it afterwards. So this is how many joules, but I'll convert it now electron volts. So minus 14.4 electron volts. So it requires 14.4 electron volts to be freed and keep the kinetic energy the same. Now in real life it doesn't need this, it doesn't need as much energy as this to be freed, because when you free it you often don't care if it has kinetic energy. In fact, you would be happy if it had no kinetic energy. So you won't need as much as this. You just need this much if you would like it to keep its speed the same after being freed. The last one's a little bit hard. I wonder if anybody got number 4. A proton is fired at a speed v towards... proton is fired towards 3 protons. Oh, stupid English. As the electron approaches the proton, it feels... Yes.
As the proton.
Well, which way did you do it? As a proton and 3 protons? Or an yeah, so it has to have been a proton. Yeah, so I need to delete that. That should have said as the proton approaches. So what I had here was 1 proton and then 3 protons. And what will happen is, as this gets closer, it will slow down, stop, and then get pushed back away here. Yeah. Now, let's have a look here. What is the V if the closest it gets is 1 nanometer? So, let's have a look at the energy here. What energy does this have here? No. If this is far enough, if this distance is big enough, then this has only kinetic energy, because it's not trapped, or in other words, the distance is so great it feels no effect of the protons, so it has only kinetic. Now, that's definitely not the case here. It has no kinetic, but what does it have? It has potential, because it's like a spring that gets compressed and stores up energy to release it back as kinetic. So in other words, the kinetic equals the potential. Now, we have to be careful here and ask ourselves, is this a plus or a minus? It's a plus, because it's definitely not trapped. In fact, it's the opposite. It's being pushed away. Right, so V would equal 2K Q over m or squared square root. Let's see what we get. Two k q, which is 23, times q, which is 3 protons. Mass of a electron, proton, and then the distance is, now I made a mistake. What's my mistake? No, what's my mistake? No, I did, 1 nanometer. What's my mistake? What's my mistake? Yes, what's my mistake? Okay, I'll be calm. No.
No r squared.
Thank you. Did you write an r squared? No. Okay. Nano. 1 nanometer. So I guess this would be probably pretty fast, isn't it? What? That's puny speed. Oh, okay, that's better. Oh, where's it gone? I lost it. Oh. Thank you, Monica. Yeah. I know. Okay. Now, there we go. 28.8 kilometers per second. Wait, what did you get? You just saw me type it in directly here. How could I be wrong? There's no I typed in wrong here, is there? No. This is all good. Yeah. Momentum change? Momentum change only works if there's no external force. There is an external force, the proton's repulsive Coulomb force.
So they have force there.
So there is a force, yeah. So you can't use momentum change. Oh, well, why do you mean use momentum change?
Every minus m over 3, right?
Yeah.
Force is acting over there.
I see, so you want to say, no, I think I get you. You could maybe say something like force, which equals k q over r squared equals delta p over delta t. That's interesting actually, KJ. Let's have a look at what answer you get. Because here, oh, but I suppose you don't know the delta t. Because you don't know the time here and here.
Yeah, so I thought you that was the time.
I suppose we could, let's just see what happens if we assume delta t is roughly 1 second. Let's just see what happens. So you get k q over r squared. This will be mv minus mu over 1. But this is 0. It's actually this that you want. I won't care about the minus. I'll just cancel all the minuses. So you basically get v, or u as you called it, is roughly k q over m r squared. Now that's kind of similar, but there's no 2. And yeah, I wonder what happens. No, I don't think it'll be the same because we had to assume something about the time. Whoops. Perfect. Nano is -9, isn't it?
Square.
Oh, thank you. Oh, but that would make it even smaller, though. And I again with the
No.
yeah. Oh, caramba. Whoa. Yeah. So I think this perhaps is Wrong. If I kept the delta t, then I'll have a delta t here. So there's a time up the top. This time must be tiny. It must, like, the time it takes to get from the outside to the 3 protons must be, you know, less than a nanosecond. So I think this is where it will fall down for you. Yeah? You forgot the 2?
You know, because I first with F,
Yeah.
and then using MD squared over R, I got to be,
You first got F.
I don't know, because I thought when it treated that point, that 1 nanometer is feeling the same thing an electron is doing if it was 1 nanometer apart.
The force would be the same. Yeah.
So I use F equals MD squared over R.
F equals M. No, you can't use that formula. Why can't Monica use F equals MP squared over R? Anybody? No, that's not the reason. MP squared over R. Why can't Monica use that formula?
It is not.
Yeah, that's it. It's not circular motion. The proton never is in orbit of the 3 protons.
No, it's okay. Everything else was right except that two.
Yeah.
Just a small minus. Anyone could have done that.
Okay, children. We have that one finished. And so I don't forget, let me just change this to proton. What's next after this? So Newton's laws and Kepler's laws. Yeah, Newton's law, the gravity one.
What surprised you?
You came to Friday class.
Yeah, I
I
know.
heard your voice.
Yeah. How could...
He's late.
Was he?
Yeah. I heard.
Oh, he was 15 minutes late. And then we weren't sure if we should let him in.
Teacher, where are you going now?
Nowhere, I'm here.
Oh, so we can meet Bruce here.
Do you want to wait to say hi to Bruce?
Yeah, definitely.
Well, have you got a class now?
Yeah, definitely.
What?
He's asking everybody. So because there's 2 lessons left and you didn't have any time to do the one today, obviously, because you have to savour it, next physics class will be a tutorial. Guys,
Yeah.
next physics class, which is when?
Tomorrow.
1 or 2 hours.
Tomorrow.
That's tomorrow.
2 hours.
Right, the first class...
Tomorrow.
Tomorrow.
Anyway, the next physics class will be a tutorial and then we finish fields. Is it Wednesday? It's Wednesday.
Oh, Wednesday morning.
What?